Okay, last time we talked about the mean value theorem and applications of mean value theorem. Let's recall what the mean value theorem says. Mean value theorem says if a function satisfies two conditions, i.e. continuous on closed interval and two, differentiable on open interval. So let's see. Then the conclusion is, then we have the derivative. So derivative f derivative at C, where C lies in the two endpoints, A to B. F derivative at C equal to the slope. Okay, the right side is slope. Change of y values over change of x values. So this is the mean value theorem. I.e., we can estimate, we can get information about the change of function values fb minus fa by the product of average derivative, okay? F derivative times C times B minus A. And we give a physics explanation of this mean value theorem by average velocity. And we proved that mean value theorem by rule theorem. There are many applications of mean value theorem. For instance, prove that certain equations has only one real root. Okay, i.e., we first, the key to do this kind of problem is we first show that there exists one root by intermediate value theorem. I.e., we pick two numbers such that the two function values, they are, one of them is negative, one of them is positive, and then by continuity there should be a zero. And then we use mean value theorem actually to show that there exists exactly one real root. So the way to do that is we suppose that there are two roots and then find a point derivative to be vanishes. Okay. However, for certain situations, the derivative cannot be vanished. So for instance, for this example, the derivative does not vanish. And then we get a contradiction. So that we can prove that this function cannot have two real roots. So this is what we did last time. And then we have increasing decreasing test. Increasing decreasing test. Okay, increasing decreasing test says if derivative is positive for all x value in interval I, then the function is actually increasing. Now, if derivative is negative, then the function is actually decreasing on this interval I. The proof actually use mean value theorem. Now from increasing decreasing test, we can determine the interval of increase or decrease, i.e., we take a derivative of the function and then try to find on what interval that the derivative is positive. If the derivative is positive, then by increasing decreasing test, then we know the function is actually increasing. If the derivative is negative, then the function fx, original function fx, decreases. So this is increasing decreasing test. From increasing decreasing test, we can determine local max and the local minimum of a function. Now you see, if we have a local max, at local max, for instance, this graph, at local max, -1, you see, on the left side of -1, we know the function is actually increasing, okay? So its derivative should be positive. On the right side of -1, it's decreasing, so its derivative should be negative by increasing decreasing test. So we get a condition when we achieve local maximum, i.e., if the derivative change from positive to negative, then we know the function attains local maximum. Okay. Now at local minimum -3, at local minimum -3, you see the derivative, the left side is decreasing, so the derivative should be negative. The right side is increasing, so its derivative should be positive. So we know the derivative first decreases, and then we know that the derivative should be changed from negative to positive at the local minimum. Okay, so to summarize, then we get first derivative test, which says the following. If the derivative change its sign from positive to negative at number c, then the original function fx attains a local max at c. The second part says if the derivative changes from negative to positive at c, then f attains a local max at c. Okay. Now part C says if the rate does not change sign, i.e., the function is actually is increasing all the time or decreasing all the time, then we have no local max or local min at the number C. Okay, we give some example. We give examples of this increasing decreasing test. Okay. Okay. We give several examples that some applications of increasing decreasing test. How to find local max, local min. Now we already give examples of the first two cases, and now let's see the third cases. Now when fx is x cubed, this example. Now let's plot the graph of x cubed. Let's plot the graph of x cubed. Now if you plot the graph of x cubed, it will be looks like this. This is x, and this is y. Now it passes through origin O. Now it looks like this. Okay, so this is y equal x cubed. Okay, now you see it's now first we take derivative. F derivative x is x cubed derivative, which is a 3x squared by power rule. Now you see x squared is always non-negative, so this is always non-negative, greater equal than 0. Then you see the function is actually increasing. So by increasing decreasing test, fx is increasing all the time. Okay, because derivative is positive, non-negative for every x. Okay, now you see what's the critical number? The critical number. Now f derivative, let fx derivative be 0, then we get a 3x squared to be 0. Remember, the critical numbers are the x coordinate such that the derivative vanishes. Okay, the x value such that the derivative vanishes, or the derivative does not exist. Okay, so here we get 3x is 0, so this implies x is actually 0. Okay, now you see at x equals 0. Okay, the derivative f derivative does not change sign. Okay, does not change sign. Because it's left side is positive, right side is positive. Does not change its sign. So then we have low, at origin O. You see, at origin O, there's no maximum, there's no minimum, because the functions keep increasing. Okay, there's no maximum. There is no maximum, no local max or local min at x equals 0, i.e. origin O. Okay. This is the first derivative test. Okay. Let's see more examples. So suppose fx is 3x cubed, 2x cubed, sorry, minus 3x squared minus 12x. Find the intervals of increase or decrease. Find the intervals of increase or decrease. Now, for what interval that fx is increasing, now we need to use increasing decreasing test. Okay, so we first take derivative. So a b find the local max, local max, local max, and local min. Okay. Okay, let's find increasing or decreasing intervals. Okay, so we first take the derivative. So f derivative of x, so we take the derivative for every terms by distribution property. So we get by power rule. So this is we get 2 times 3x squared minus 3 times 2x minus 12. So this will be 6x squared minus 6x minus 12. So this will be factor out of 6, x minus 2. So this will be 6, x minus 2, x plus 1. Okay, factor is quadratic. Factor is quadratic. Then what we get is, you see, it has two roots. It has two roots. So f derivative to be 0, then we get 6x minus 2x plus 1 is 0. So you get the factor x minus 2 is 0 or x plus 1 is 0. So we get two roots, x is 2 or x is -1. And then we look at its factor. So these two numbers, -1 and 2, parties this x coordinate into 3 intervals. Okay, i.e. we have 3 pieces, -infinity to -1, -1 to 2, and 2 to positive infinity, 3 pieces. And then we look at its factor. We look at its factor of this derivative. Okay, x derivative minus x minus 2x plus 1, and then f derivative and fx. Okay, and I see the sign of its factor. Okay, now x minus 2 on its interval. Okay, x minus 2 on its part. So x minus 2 when x is less than -1. So this is actually negative. From -1 to 2x, then x minus 2 is negative, less than 0. From x to be 2 to positive infinity, x minus 2 is positive. Okay, positive. Similarly, we work for x, work out x plus 1. X plus 1, this should be negative. This should be positive. This should be positive. Okay, so their product. This is positive. Negative times negative, we get positive. Negative times positive, so this is negative. Positive times positive, then we get positive. Okay, positive. Then by increasing and decreasing test, we know derivative, the first interval, -infinity to -1. So the derivative is positive, so fx is increasing. Okay, now from -1 to 2, f derivative is negative, so we have fx should be decreasing. Okay, similarly for the interval 2 to infinity, positive derivative, so f is increasing. Okay, so a rough graph is, so f is increasing, then decreasing, and then increasing. Okay, so here we have, you see, so here we have, this is the boundary is -1, x is -1, and here this is this. So sorry, it should be. So this part is actually local minimum. Okay, decreasing and increasing. So this is actually 2. Okay, now we find, so we know fx attains local max. Okay, increasing, decreasing, and then increasing. Local max at x to be -1. Okay, so f -1 plug in. Remember the original fx is 2x cubed minus 3x squared minus 12x. So plug in -1, plug in -1. So this we get 2 times -1 cubed minus 3 times -1 squared minus 12 times -1. So it's more easy now. So it's -2 minus 3 plus 12. So this is the 12 minus 5. We get a 7. Okay, we get a 7. So it's local max. Local max. And what is local main? So fx attains a local main at x equals 2. And then we find the value, function value f2 to be plug in 2. So it's 2 times 2 cubed minus 3 times 2 squared minus 12 times 2. So this is the 2 to the power 4, which is 16. Minus 3 times 12, 3 times 4, 12. Minus 12 times 2, 24. So this is a 16 minus 36. So we get this is -20. So this is actually local minimum. Local minimum. This is local minimum. Okay. Then we went down for local max and local min. Okay, now the next step, you may ask, we know what property that a first derivative can true. Now the next question is, what property does f second derivative tells us about f? Okay, the next question is, what is, okay, question, what's f second derivative see about f? About f. Okay, f second derivative, remember f second derivative is derivative of derivative. Now to talk about what properties that f derivative, f second derivative can true about this function f, we first give a definition. Okay, if the graph of f lies above its tangent line, lies above all of its tangent lines on an interval I, then we see f, then it is called concave up, okay, concave upward, I. Now similarly, if it lies below all its tangent lines, okay, if the graph of f lies below all its tangent line on its interval I, then it is called, concave down, okay, concave downward on I, okay, concave up, concave down. Now, for example, okay, example, y equals fx to be x squared. x squared. Now you see, if we plot the graph, okay, if you plot the tangent line, now you see the graph actually lies above its tangent line. Okay, so lies above its tangent line. Now at any point, you see, at any point, if you take it, if you plot tangent line, if you plot tangent line at any point, it lies above its tangent line. So you see, in this case, so the graph actually is concave up, okay? It concaves up, okay? Fx, the graph lies above all its tangent line, all its tangent lines. This by definition, according to definition, this implies it concaves up. The graph concaves up, concaves upward, okay? Concaves upward. Now concave down. Now similarly concave down. Now example. Y equals fx to be negative x squared. Now if you flip it downward, if you flip it, now multiply -1, you flip with respect to y-axis, with respect to x-axis. Then what you get is this. Okay, this is x, this is y. Now at any point, if you plot tangent line, you see it lies below. Okay, or its graph, okay, its graph lies below all of its tangent lines. Then by definition, according to definition, it concaves downward. Concaves downward. Okay. So this is concavity. Now, what's actually second derivative contours is actually the concavity of graph f. Okay, so concavity test. The concavity test. Concavity test says the following: if second derivative is positive, okay, part A, if f second derivative of x is positive on an interval I, for all x on an interval I, okay, in an interval or in I, then the graph of f concaves up, okay, concave upward. Then the graph of f is concave up, concave upward on the interval I. Okay. Now part B, if second derivative is negative, if second derivative of x is negative for all x in an interval I, then the graph of f is concave downward. Okay. Now you see on the examples that we did. Example. The examples that we did. Okay, fx is x squared. Now its graph, we already know it concaves up. Okay, it concaves up. Okay, sorry. Okay, it concaves up. Y equal x squared. So it's just a rough graph. Okay. Now you see, we already know it's concave up. Now if you check second derivative, so second derivative, So f(x), f derivative x is x squared derivative. By power rule, we get a 2x. Okay. Now, if you take second derivative, take a derivative again. So this we take derivative of 2x, then we get a 2. Okay. Now 2 is of course is greater than 0. So by concavity test, we know the graph actually concaves up. Okay. So concavity test. Concavity test tells us that the graph of f concaves up. Okay, concaves up. Concaves upward. Okay, by increasing by concavity test. Okay, similarly, the example. F(x) is negative x squared. Now we know its graph is actually concave down. Okay, concave down. Now if you check, okay, f derivative is negative 2x. F second derivative, you take the derivative again, which is negative 2x derivative, you get actually negative 2, which is less than 0. So it's indeed by concavity test. Concavity test tells us it concaves down. Okay, the graph of f, the graph of fx concaves downward. Concaves downward. Okay, more examples. Y equals sine x. Y equals sine x. Now find its concavity. Now to determine its concave up or concave down, then we need to find a second derivative. So y derivative is sine x derivative. Then we get a cosine. Okay, check a derivative. Now second derivative, we take the derivative again. So derivative, cosine derivative, we get negative sine x. Okay, negative sine x. Okay. Then you see we find concavity. Okay. Now from you see when second derivative is negative sine x, if this is positive, then this implies sine x is negative. Sine x is negative. When sine x is negative, now we just plot one period. So from 0 to 2 pi, okay, sine x is a negative when x is in pi to 2 pi. So this is a negative. So we know, so if we do one period, so y derivative is less than 0. So it's concave downward. Okay, concave down. So this implies sine x is positive. Okay, sine x is positive. So this means x lies in between 0 to pi. Okay, so we know for one period. So it's 0 to pi and pi to 2 pi. So second y derivative, y second derivative, and y. Okay, I need to make more. Yeah, there should be more part. Okay, let's just use concavity. So this is the concave when x from 0 to pi. Then this is negative. This is positive. So it's concave up. Okay, concave up. Concave up. This is concave down. Okay, concave down. Now, if you plot his graph, now, of course, you also need to consider increasing, decreasing. Now, okay, y 0 to 2 pi. So suppose this is a Suppose this is y. Pi, 2 pi, pi is around 3, 1.4, etc., etc. 2 pi is around 6, little more than 6, okay? 1, 2, 3, 4, 5, 6. So suppose this is 2 pi here. 2 pi here. Pi is 1, 2, 3, 3.14. So this is around pi. Half pi is 1.5. So this is pi over 2. Now it's concave down. Okay, concave down. Be careful, it's concave down. Concave down. Okay, concave down from 0 to pi. Sorry, did I make a mistake? Yeah, from 0 to pi is concave up. Okay, so this is a concave up. Sorry, this should be concave down. This should be concave up. Concave up. Okay, concave down. Okay, if you plot the concave down, be careful, it's concave down. So concave down, the maximum is 1. So it's concave down. Concave down from 0 to pi. Okay, and then concave up, concave down to concave up, the change, okay, change. So the minimum is -1. Okay, so this part is concave down. It concaves down, concave down, downward. Now this part it concaves up. Concaves up. Okay, it concaves up, upward. Okay. Oh, what I did? Always, concave downward. Sorry. This is concave upward. Okay, because if you take tangent line, you see the tangent line lies above. So tangent line lies. So the graph lies below the tangent line from 0 to pi. So it's concave down. Now from 0 to 2 pi is concave upward. So lies above is tangent line. Okay, concave upward, concave downward. Now a warning is the notation of concave up and concave down. Different people actually use different notation. Sometimes that people define concave up, actually define concave up to be concave down. So you need to really be careful, okay? Other people may use different notation, okay? In some textbook, they may use different notation. So sometimes concave up, concave down can be confusing, okay? So you need to be careful. Be careful. Okay, you see here at pi, at the point pi, at x equals pi. So at the point pi 0. So the point, so we had the point pi 0. The graph, you see, the concavity changes. The concavity changes of the graph. Changes, okay? Left side of this point, okay, let's see this point. So left side of this point pi 0 is concave downward, okay? Right side of this point is concave upward, okay? Then we call, in this situation, we call it an inflection point, okay? So this is actually an inflection point. So pi 0 is an inflection point. Inflection point. Definition. What is an inflection point? A point on the curve is called an inflection point. Okay, a point P on the curve, on the graph of the function, or on the curve y equal fx, is called an inflection point. inflection point if the graph changes its concavity, okay? If the graph or the curve, if the curve or the graph, if the curve changes its concavity, concavity at P. So you see the example that we did for sine x, the point pi 0 is an inflection point. Okay, is an inflection point. Okay. Example. Okay. This example. Fx to be x power 4 minus 6x squared. Okay. Find its so find interval of increasing decreasing. So increasing decreasing question. Find increasing decreasing intervals. Concavity. Local max, local min. Okay. Inflection points. Okay. Then plot is a rough graph. Okay. So we work out these properties for this function. Now the first of course we take derivative. Now derivative by power rule. So this will get a 4x cubed power rule. Now 6x squared is derivative is actually 12x. Now if you factor out the 4x, they get x squared minus 3. Okay, so this will be, now we find critical numbers. To find the critical numbers, okay, critical numbers. So we get the factors, so we get to solve, x is 0 or x squared minus 3 is 0. So we have x 0 or x equals plus minus root 3, okay, plus minus root 3. Now you see we have three critical numbers. Critical numbers are 0, negative 3, 0, positive root 3. Okay. Now these critical numbers partition this x coordinate into intervals, and also we also need to find when the second derivative values is. Okay. Then take second derivative. Now first derivative is 4x cubed minus 12x. So we take a derivative, then we get, this is the 4x cubed derivative minus 12x derivative. So this is the 12x squared minus 12. So if you factor out 12, so this is 12x squared minus 1. So this will be 12x minus 1, x plus 1. Okay, so that second derivative will be 0. Then we get this 12x minus 1, x plus 1 is 0. So we have two roots, x minus 1 is 0 or x plus 1 is 0. So we have two roots, x equals 1 or x equals negative 1. Okay, then you see the next step is we put all the numbers on the number line, okay? So we have 0, negative 1, okay, positive 1. Then root 3 around 1.7, okay? So it's root 3 here, then negative root 3. Then you see all these numbers parties this x coordinate, the number line, in terms of intervals, okay? It parties it in terms of intervals. And then we will try to look at for its factor and see how f derivative and second derivative, whether they are positive or negative. Okay, so we parse this thing into intervals. Okay, so the interval is negative infinity to negative root 3, and then negative root 3 to negative 1, negative 1 to 0, 0 to 1, 1 to root 3, and then root 3 to infinity. Okay, so the factors, you see, the factors, okay, so f, so remember, let me write here, f derivative is 4x times x squared minus 3. Now f second derivative is 12x squared minus 1. Okay, x squared minus 1. Now you check on each interval is positive or negative. Okay, so just right here, x squared minus 3. Now x squared minus 1. Okay, so f derivative, f, maybe we just right here, f derivative, f second derivative is equal to 12. So this is actually f second derivative is 12x squared minus 1. Okay, let's plot this table. Okay, so this is the, okay, you see here we plot this table. Okay, now x, the factor x, whether it's positive or negative, so it's negative, 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 positive, positive, positive. Now x squared minus 3, x squared minus 3, you'll find out its interval whether its factor is positive or negative. So when x from negative infinity to negative root 3, and this is actually not hard to determine. This is negative, and this is a positive. This is positive, 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 negative. And then f derivative is the product of these factors, okay? And then multiply a positive factor 4. So this is the negative, negative. So we get a positive, okay? Negative, positive. So negative, positive, their product is negative. Negative, positive is negative. Negative, positive, positive is positive, their product. Positive, positive is positive. Positive, negative is negative. Okay? Second derivative, 12x squared minus 1. X squared minus 1, you check, okay? Positive, positive, negative, negative. And then fx. So first derivative tells us increasing, decreasing. So here, the first interval, negative infinity to negative root 3. So this is actually increasing, okay? Increasing, increasing. Concave up or concave down. So we know second derivative is negative, okay? Second derivative is negative, so it's concave down. Okay, so the interval negative root 3 to negative 1. So first derivative is negative, so it's decreasing, okay? Decreasing. Now second derivative is negative, so it's a concave down. Okay. Now first is negative 1 to 0. F derivative is negative, so it's a decreasing, okay? Now concavity, so second derivative is positive, so it's concave up, okay? Concave up, concave upward. So it's concave up, concave down, concave downward, okay? So it's increasing, increasing, decreasing, okay? Now how this function looks like, so here we see change from, so the interval from negative infinity to negative root 3 to negative root 3 to negative 1. So it changed from increasing to decreasing. So we have here, we have increasing, decreasing. So we have local max, okay, local max. Here we have local main, okay, decreasing, then increasing. So we have local main. And then here increasing, decreasing. So here we have local main. Sorry, local max, increasing and then decreasing. So it's local max here. Okay, now the combinations of concave up, concave down, increasing, decreasing. So this concavity and increasing, decreasing has two combinations. So increasing, let's do it. Increasing concave up. Okay, concave up. Increasing concave up. Okay, this is increasing concave up. And then increasing concave down. Increasing concave downward. Concave downward. So it's increasing concave downward. So it looks like this. Okay, increasing concave down. And then decreasing concave up. Decreasing concave up. Decreasing concave up. Okay. Decreasing concave down. Okay, concave down. Decreasing concave down. Okay, decreasing concave down. Decreasing concave down. Okay, decreasing concave down. So there's four cases. All right. Now we will apply these four cases to the function here. Okay, to the function here. Now to plot this graph, we need to find local max and local min. Okay, so we find the value at -3. Okay, at 0. Okay, so let's plot this graph. Now let's plot the graph. Maybe I plot the graph here. Let me insert some space here. Okay, let's see. Okay, here. Okay, let's insert certain space here. Okay. Okay, now let's see what the maximum and minimum is. Okay, maximum and minimum is. Now the function here is fx is x power 4 minus 6x squared. So the local max f -3. So here, first of all, f is even function, is symmetric. So we only need to plot half of its graph. And then the other half, we can apply symmetry, okay, with symmetry. Even function is symmetric with respect to y-axis, okay. So we can use symmetry. So plug in √3. So this is the √3 to the power 4 minus 6 √3 to the power squared. So it's 3 squared, so it's 9. 9 minus 6 times 3, so it's 9 minus 18, so it's -9. So local max is -9. Now local main, let's see local main. F0 is plug in 0. This is very easy. Plug in 0. 0 minus 0 with 0. Okay, now let's plot this graph. Let's plot the graph. So let's insert a little space. Okay. This is the x, is the y. Okay, from remember the interval notation. Let's do the interval notation. Let's plot, for instance, let's just plot the negative part. So we have -1 here, and then -√3. -√3 is around root 3. Root 3 is around 1.732, etc., etc. So it's slightly less than 2. So this point is maybe here. This is the negative root 3. Okay. Now you see at when x is negative root 3, y value is negative 9. Okay, so negative 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's around here. It's around here. When x is a negative 1, when x is negative 1, when x is negative 1, you find its value. Okay, so f negative 1, f negative 1, f negative 1, which you get y minus 6, which is the negative 5. So when x is negative 1, it's negative 5. 1, 2, 3, 4, 5. So it's around here. 1, 2, 3, 4, 5. So around here. Just plot a rough graph. Okay, just plot a rough graph. Then from negative infinity, you see, from negative infinity to root 3, it's a concave, increasing, concave down, increasing, concave down. Okay, increasing, concave down, increasing, concave down. So it's a increasing, concave down. So increasing, concave down. So increasing, concave down. Look like this. Okay, increasing, concave down. Increasing. Then from root 3 to negative root 3 to negative 1. So the second interval. So it's decreasing, concave down, decreasing, concave down, decreasing, concave down. Okay, did I get a mistake? I think it seems to be mistake. Yeah, if it's decreasing, then it should be smaller. Let's see where we get something wrong. Where we get something wrong. Where we get something wrong. Oh, here, yeah, sorry. Yeah, you see here, this is wrong. X squared minus 3 in this interval. X squared minus 3, sorry. X squared minus 3, this part should be positive, okay. This part should be negative. Okay, this part then should be negative. This part should be negative. Okay, oh, Jesus. This part is positive. Oh, my God. Oh, yeah, this is totally wrong. So this is negative. This is positive. This is positive. Ah, Jesus. Okay, now we need to change it. We need to change it. Jesus. So it's the concavity does not change. The concavity does not change. Let's see the concavity. Oh, what I did. Whew. All right, the concavity is also wrong. Sorry, Jesus. Concavity is also wrong. This is negative. This is negative. This is positive. This is positive. Ooh. All right. Then we need actually totally change it. Sorry, what I did. So it's a decreasing, concave up. So this will be increasing, concave up. Now concave down, concave down, concave up, concave up. Sorry. Now now this increasing. This will be decreasing. Now this will be decreasing. This will be increasing. Okay. So it's decreasing, increasing. So we have local minimum. So this we have local maximum. This we have decreasing, increasing, local minimum. Yeah, then it makes sense now. Then it makes sense now. Now from -3, sorry, this part should be changed. Now from negative infinity is concave up, decreasing, concave up, concave up, decreasing, concave up, decreasing. So concave up, decreasing, concave up, decreasing. Then from -3, concave up, increasing. From -3 to 1. So it's concave up, increasing, concave up, increasing. So concave up, increasing. So remember concave up, increasing. So concave up, increasing. What the concave up, increasing looks like. Okay, concave up, increasing. Okay, concave up, increasing. So concave up, increasing. Then from -1, from -1 to 0, from -1 to 0, it's increasing, concave down. Okay, increasing, concave down, increasing, concave down. Okay, increasing, concave down, increasing, concave down, increasing, concave down. Okay, increasing, concave down, increasing, concave down. So use increasing. So when x 0, so it's 0. So increasing, concave down. So it's increasing, but it's concave down. Okay, concave down. Okay, increasing, concave down. Okay, then actually we are done. Now the other pieces follows by symmetry. Follows by symmetry. Now for the positive part, x being positive part. So what we do is this is the 1, this is √3. This is 1. Now we flip it by symmetry. We flip it by symmetry. Okay, flip it by symmetry. Then you see it's again -1, 9. And then we are done. Then we're done. Okay, so this is a graph of the function. So we find local max, local min, concave up, concave down its property. Now, what is its inflection points? Okay, what is inflection points? Inflection points. Now, inflection points is where the concavity changes. You see, this part is concave up. Okay, concave up. Now this part is from -1 to 1 is concave down. Okay, -1 to 1, concave down. And then from all the way to infinity, this is the concave up. Okay, concave up. Now you see the concavity changes at when x value is -1 and 1. Okay, so when x is -1, y value you plug in is -5. Okay, and by symmetry, out of 1 -5, the graph changes its concavity. The curve changes. The graph changes its concavity. So we have 2 inflection points. Inflection points. By definition, we have 2 inflection points. Now, inflection points is a point on the curve. Okay, inflection point is on a point on the curve, not just x coordinate. Okay, so we get 2 inflection points. Then we are done for this problem. Okay, then we are done for this problem. Any questions for this problem? Okay. Okay, more examples. Let's do some more examples. Okay, this example. Y to be arctan-x. Find its concavity. Okay. Now we take a derivative and a second derivative. Okay. So y derivative. is, now we take a derivative of y. Now y derivative, arctime derivative. Remember arctime derivative is, okay, we did arctime derivative. This is from derivative table, 1 over 1 plus x squared. Now to determine its concavity, so this is all, you see this is positive all the time. So this is actually increasing all the time. Increasing all the time. Now we determine its concavity, so we need to take a second derivative. So we take this derivative. Now we use quotient rule. Or you use chain rule. Okay, you use chain rule. So it's a negative 2x over 1 plus x squared. Okay. So you see, it's concave up, concave down. Okay. Second derivative is positive if negative 2x is equivalent to x is negative. Okay. Second derivative is less than 0 if less than 0. This is equivalent to x positive. So it's concave. So this means, remember, it's defined. It's the okay, i.e. from negative infinity to 0, from 0 to positive infinity. So second derivative is when x less than 0, this is positive, this is negative. So y is concave up. This is concave down. So it's increasing. Y prime. So y prime is always positive, so it's always increasing. So if you plot this graph, remember we have a horizontal asymptotes. Limit x approaches infinity, arctime x. This is actually pi over 2. So we have horizontal asymptotes. This point is pi over 2. This point is a negative pi over 2. This point is negative pi over 2. Okay, so when x is positive, so it's concave down. Okay, increasing concave down. Okay, increasing concave down. When x is negative, it's increasing concave up. Okay, increasing concave up. Okay, so this is arctime x. So this is y equal arctime x. This is the graph of arctime x. So it has a horizontal asymptotes. Okay, limit x approaches negative infinity. Arctime x, its limit is actually negative pi over 2. So the graph get object close to negative pi over 2. Okay. Okay. Now let's talk about the, let's give several examples, and then let's see how to, sketch a graph that satisfies all the given conditions. Okay, example. Now suppose we give some conditions of a function, and then try to plot a graph of a function that satisfies all the given conditions. Okay, suppose f derivative is positive for all x not equal to y. Vertical asymptotes. X equals to y. Now f second derivative is positive if x less than 1 and x greater than 3. F second derivative is less than 0 if x between 1 and 3. Okay, how do we plot a graph that satisfies this condition? Now, first of all, try to organize the information of a derivative and a second derivative into a table, okay, such that you do not mess things up. So here the boundary values. First of all, try to look at the x values, okay? Try to look at x values. You see here the x values, the special values of x. Here we have two numbers, 1 and 3. 1 and 3. Then you see these 2 points, 1 and 3, two numbers, partition this x coordinate into three intervals. So we have negative infinity to 1 and 3, 1 to 3, and then 3 to positive infinity. And look at each interval, okay, derivative and second derivative, and see f derivative, f second derivative, and fx. Okay, now you try to keep everything into a table. Okay. From negative infinity to 1, i.e. x less than 1. Now we know derivative, first derivative is always positive, so it's always positive. Now second derivative is positive from if x less than 1. So less than 1 is positive, or greater than 3 is positive. Otherwise, from 1 and 3 is negative. Okay, so you see, then we determine fx. fx first derivative determines increasing decreasing, so it's increasing and concave up. This is increasing, concave downward. This is increasing, concave up. Okay, now increasing concave up, looks like this. Increasing concave down looks like this. Increasing concave up looks like this. Okay, look like this. Okay, increasing concave up. Then let's just plot a graph that combine all the pieces together. Now the key information is 1 and 3. So this is 3, this is the 1. Okay, less than 1 is concave up. Less than 1 is now we have vertical asymptotes. So let's just plot concave up, increasing. Concave up, increasing. Now there's a lot of freedom. And then from 1 to 3, 1 and 3 is increasing, concave down, increasing, concave down, increasing, concave down. Maybe we do it like this. Increasing, concave down. Okay, increasing, concave down. And then from 3 to infinity, now it's changed from increasing, it's increasing, concave up, increasing, concave up. Now you see we have inflection points, then we are done. Okay, this is xy. Okay, inflection point. So at this point, we have inflection point where the concavity changes. Inflection point when x is 3. Okay, we are done for this problem. Okay, maybe just one more problem on graph sketch. Okay, one more. Okay, let's see this. Example. F derivative is positive if the value of x is bounded by 2. F derivative x less than 0 if the value is greater than 2. F derivative at -2 is 0. Limit x approaches 2. F derivative is actually infinity. Okay. Now f derivative is positive if x not equal to 2. Okay, try to keep all the information in a table. Okay. Okay. So here the key information is 2. The key point is 2. Okay. So now if you put the number 2 on the number line, so it has 2 intervals. Negative infinity to 2. And then 2 to positive infinity. Also, okay. Also, we have negative 2. Sorry. Negative 2. Negative 2 to 2. And 2 to positive infinity. F derivative, F second derivative. And fx. Try to plot this table. Try to plot this table. And then put everything in this table. Okay. Try to put everything in this table. Okay. When x value bounded by 2, when x value bounded by 2, so this means x from negative to 2. So first derivative is positive. Okay. First derivative is negative if x value is beyond 2. Okay. Then second derivative is always positive. Positive. Then you see we have this decreasing concave up, increasing concave up. This is decreasing concave down. Oh, sorry, concave up. Okay, now if you plot the graph, decreasing concave up, decreasing concave up, decreasing concave up, looks like this. Okay, increasing concave up, increasing concave up, and then decreasing concave up, decreasing concave up. And then we piece all the information together. We group all the information together, and then plot a graph. Plot a graph. Okay. X. Well, this is the y. Now negative 2 to 2. Okay. Now f derivative at negative 2 is 0. Tells us f derivative at negative 2 is 0. This tells us at negative 2 we have a horizontal tensor line. Okay. Horizontal tensor line. Horizontal tensor line. From negative infinity to negative 2, it's it's decreasing concave up, decreasing concave up, decreasing concave up. Then from negative 2 to 2, it's increasing concave up. Now, what this information tells us? Limit f derivative of the value is actually infinity. X approaches the 2. Now, this tells us that the it's increasing. So the derivative at 2 is really big. So we have vertical asymptotes. Vertical asymptotes at 2. Okay. Decreasing concave up. Okay, so we have, so this tells us this derivative approaches infinity of value at 2 tells us we have vertical asymptote at x equals 2. Okay, so so we are done for this plot. Okay. Okay. Now, when you plot a graph, the key information that usually you take into consideration is increasing, decreasing, concavity, concave up, concave down, and then local max, local min. Okay, local max, local min, and geometric property, horizontal tensor line, vertical asymptotes, or horizontal asymptotes. Okay, if you combine all the information together, and then you can try to piece all the information together, group all the information together, and plot a reasonable graph. Okay. Any questions?